Swayam Prabha. Digital India. Educated India.
This is lecture number 10. Hello everyone, welcome back, and we will continue the discussion that we had that we are having regarding the governing equations for fluid flows. So, in the last class we basically derived the momentum equations. Okay. So, what we did is basically you had conservation form. So, this is del rho ui by dt plus del by del x j rho ui uj is equal to d tau I j by del x j, okay, and plus rho and b I, right. And we said that this is our time rate of change. So, this is the temporal term, this is the convection term, okay, and this is the stress term which is related to the our viscous diffusion, okay, and finally we had this the body force term, okay, and then we also related this tau I j to the strain rate, right, and we basically what we found out is tau I j equal to 2 mu E I j and plus lambda, and that will be delta I j del u k by del x k, right, where E I j is the strain rate tensor, symmetric part of the strain rate tensor, which is nothing but half del u I by del x j plus del u j by del x I, right. So, 2 I j E I j will be del u I by del x j plus del u j by del x I, right. And we said that mu is the first coefficient of viscosity or the molecular viscosity as we know it, and lambda is your bulk viscosity, right. It is the second coefficient of viscosity, and if you write we also found that this lambda plus 2 mu by 3, okay, this is called the bulk viscosity. Let us represent it using beta. So, this is the coefficient of bulk viscosity. Bulk viscosity, okay. So, then we said that for normal flow conditions, if the flow rate is basically the speed is not very high, it is not in hypersonic region, or if the gas is let us say monatomic, in that case the beta almost goes to 0 and the lambda becomes minus 2 mu by 3, okay, and this was called the Stokes hypothesis, okay. So, this is exactly true for monoatomic gas because they have only the translation degree of freedom, but when you treat the diatomic and triatomic gases, then it becomes an hypothesis. In that case also this lambda plus 2 mu by 3 or basically beta is nearly 0, okay. If beta is not 0, then what happens that in most cases the delta dot u grad dot u is equal to 0. So, the multiplication of this lambda plus 2 mu by 3 del dot u goes to 0, right, which is the term that you have here, okay. You have lambda multiplying by del u k by del x k, which is del dot u, right. So, using this hypothesis you get this lambda equal to minus 2 mu by 3, right, and if the flow is not hypersonic you can use this hypothesis, okay, and for most flow condition it works, okay. But if the change is in the thermodynamic condition is very rapid and the system is not able to adjust to that thermodynamic change, then you have to basically look for the variation in the bulk viscosity also. and that usually happens in very high speed flows like in hypersonic flows or even high Mach number flows, okay, high supersonic flows, right. So, if you use all those conditions, okay, there was another term here which was the P delta Ij, right. So, this is minus P delta Ij, okay. So, this we had termed as the hydrostatic stress, and these two are basically the deviotic stress, right. So, if you combine all of these, then you will get this final expression rho u I u j is equal to minus del p by del xi, okay, and plus you can write del sigma ij by del xj and plus rho bi, where sigma ij is the deviotic part, okay, 2 mu e ij plus lambda delta ij del uk by del xk, right. So, this is your final momentum equation. You can express it in different forms, okay, and this is the differential form. Of course, you can get the integral form also from the Reynolds transport theorem, as we have got the mass conservation equation, right. Now, let us try to write it in form that is called the non-conservation form, okay. So, what do we do? This is my A, okay. So, let us take the left hand term, this is rho u I by dt plus del rho u I j u I u j by del x j, okay, and let us try to basically use the chain rule, okay. So, this will become rho del u I by del t plus u I del rho by del t, right. This is the first term, and the second term, if I take the rho u I together and u j together, okay. So, del by del x j rho u I u j, okay, and plus you will have rho u I del u j by del x j, right. This correct. So, what I am trying to do, I am trying to use this mass conservation relation to basically put it in a form where the rho is outside the, okay. So, if you collect the term, so rho u I and u j del u I by del x j, okay, that is the first term, this is the fourth term, and plus u I del rho by del t and plus del by del x j rho u j, right. We have, this is the second and third, right. Now, this term identically goes to 0 because of the mass conservation, okay. So, then this will give you this rho del u I by del t plus u j del u I by del x j, right. If you want to write in a vector form, this will be rho del u I by del t, or in more appropriately u by del t, okay, plus u dot del u, okay. So, remember this, this is very important to put a bracket there, okay, because this is not equal to u dot del u, okay. So, here we are putting the divergence of u with the del operator, okay. So, that you have the expression u del by del x and then v del by del y and plus w del by del z, okay, and depending on the direction of u, you will have u or v or w here, okay, this portion. But this is different, here you are first taking the gradient of a vector, right, if you do del u here. So, then it is a it is basically a tensor and you are taking a dot product of a vector u with that tensor. So, this is not the form that we have in the Navier-Stokes equations, right. So, now let us put it back into A, which is on the left side, okay, this is A. So, if you replace the left hand side with the expression that we had. Okay, so then it will give you rho del ui by del t plus uj del ui by del xj is equal to, right hand side remains unaltered. So, just write, let me write tau ij by del xj plus rho bi or rho gi. Okay, this is the body force. So, this is your the final form. So, this is called the non-conservation form. Okay. And please understand that there is no difference if I call this B. So, there is no difference between A and B here. Okay. The A is here and B is here. So, there is no difference between A and B. Okay. Both are the same thing, it is only the expressing it in a different way, but the A is called the conservation form and B is called the non-conservation form, and this is purely a CFD terminology, it has got nothing to do with the fluid mechanics. Okay. And when it is conservation form, so why it is called conservation form is because you can use the rho u variable inside your d by dt, okay, or even the your flux, okay, the convection term. Okay. So, this rho u becomes a conserved variable. Okay, and we will have some discussion about conserved versus primitive variable, but the advantage of using this rho u, especially in compressor flow, is that you do not have to basically separate this rho and u, and that is very useful when you do any kind of averaging or even the CFD calculation, right. So, your rho always comes with u or v or w or even the energy. Okay. So, these terms are called the conserved variables, wherever if you use u, v, w and e, okay, then these are called the primitive variables. Okay. So, in compressible solver, conserved variables are very useful, because you have the variation of density also along with other flow variation of other flow quantities, right. So, you want to arrest the variation in density and variation in velocity into the single variable, which is the rho u variable. Okay. So, that is the reason it is called the conservation form, because you have this rho u, entire rho u in your del by del t term. Okay. And non-conservation form also preserves the same I mean property if you are solving it, but it is only the your algorithm may become different if you want to solve in the non-conservation form. Further, we will discuss about the matrix form, and you will see that when you write in the matrix form, basically when you want to solve a coupled system of equations, your mass conservation, momentum conservation, energy conservation all at the same time. In that particular case, your conservation form basically helps you in a great deal, okay, in solving all 5 together. Okay. The another thing that you might want to check here is that if you really look this equation closer, okay, so what is this? So, this is mass, what is this? This is an acceleration, okay, and what is this one? This is force, right. So, this is basically your second law, basically the mass into acceleration, everything is in per unit volume, okay, as we have been discussing that the volume changes continuously. So, that is why we do it per unit volume in the fluid flows. So, it gives you the second law, which is basically mass into acceleration equal to net force, right. So, that you can easily see when you cast it in the non-conservation form, right. And once again I want to emphasize that when it is non-conservation, it does not mean that it is not conserving some variable or some value, in this case momentum, but it is only to suggest that when you are casting in a coupled form or coupled system equations, that this form is not suitable. Okay. And this is equal to you can further cast this del ui by del t plus uj del ui by del xj as the substantial derivative or the total derivative, and that will give you mass into acceleration. I mean you can write the entire thing into the acceleration. This is the Lagrangian form. Okay. So, now let us go to the Euler's equation. Okay. In CFD, many time you would be basically solving an ideal flow where you can put the viscosity to be 0, right. And we are able to solve problems without basically having any molecular viscosity, because you have in most of the CFD solutions you have something called numerical viscosity, and that is why without even putting the no slip boundary condition or ensuring that the flow velocity identically goes to 0 on the wall, you are still able to solve it, right. So, what equations do you solve on these in these inviscid flows? So, basically what we do, we ignore the viscous terms. Okay. So, if you ignore the viscous terms, okay, remember in the true situation there is no fluid which is inviscid, okay, every flow is viscous, but you get some insights about the mechanism of basically balance between different forces when you solve it in the inviscid way. Another thing is that developing a CFD solver for Euler's equation, which is the also called the inviscid equation, okay, is easy. The reason for that is the viscous force requires very cumbersome part of coding, because you have so many viscous terms available, particularly in the compressible part you have this del ui by del xj plus del uj by del xi and minus 2 by 3 basically del uk by del xk. So, you have to calculate all the gradient terms everywhere, okay, and then put in a certain form, and then you have to basically take the gradient of this entire quantity, right, and then it becomes little bit cumbersome in solving. In terms of computational cost also it is more expensive, right, because you have to determine the viscous term every time. So, in those cases you can use the Euler's equation, which is nothing but your momentum equation without the viscous term. Okay, this is basically del by del xj rho ui uj is equal to if you have some body force you can use the body force, okay, or it is just del p by del xi, or use the body force here, right. So, this is your Euler equation. So, the entire term that we had del tau ij by del xj goes to 0, because this stress is due to the presence of the viscosity, okay, presence of the molecular viscosity. So, when you start writing a code, many time you start writing first write the Euler code, okay, and then you add the viscous part, and then you can include the effect of the Reynolds number variation or the viscosity variation, right. So, this makes life very simple, but remember if you are simulating a truly I mean simulating a true flow, there is no flow which is inviscid. So, no matter how large your Reynolds number is, okay, you will still have boundary layer, okay, and so if you are solving flow on a flat plate, okay, so you will have to have a boundary layer, okay, and that you will get when you solve the Navier-Stokes equations, okay. If you solve using the Euler equation, okay, because what you are doing, you are ignoring the viscosity, so then you will not have the boundary layer, and whatever your free stream will come here only. Here the free stream will start, I mean maybe start above the boundary layer, right. So, this is from the Euler equation, this is from the this is from the Navier-Stokes equation, this is from the Euler equation, and here in the case of Euler equation you do not say that u equal to 0 at the wall, right. Here u will be 0 in the Navier-Stokes, because this is viscous forces are included, and the viscous forces will ensure that the molecules stick to the wall, right. In this case u does not go to 0 in the Euler equation, the v will still go to 0, okay. So, v is in this direction, the vertical velocity, that means that the no penetration will be ensured, but no slip will not be ensured, okay. So, what we will have is the slip boundary condition in the Euler flow. So, this is one mistake many students do, they solve the Euler's equation, but then they say that they have used the no slip boundary condition, which is not correct, okay. If you are using the Euler's equation, it will be a slip boundary condition, okay. So, now that we have the Euler equation, we can further simplify it. Let us write it for 1D flow, okay. and let us say that there is no, I mean the flow is steady, okay, then means d by dt term goes to 0, and then body forces are negligible. Okay. I mean this is a reasonable assumption in fluid flow. I mean the mostly your body force is your gravity force. You might go to MHD and all, where the magnetic force and electric forces are also important, but generally for a flow, I mean which is flowing in homogeneous x direction, okay, you can ignore the body forces here. Okay. So, this is rho b I equal to 0. So, then it will become del by del x. Remember this is a 1D flow. So, u I will be u j, this is rho u square is equal to minus del p by del x, right, all other term goes to 0, right. So, here you can see that your change in density. Okay. So, because this is 1D flow, so the del by del x can be written as d by dx, and because this is steady also. Okay. Okay, minus dp by dx. So, you can relate, you can see that you can relate the change in pressure to the your change in velocity, right. So, this can further be simplified. You can write it rho u du is equal to minus dp, right. Why we are doing this? We are trying to see where the compressibility becomes important. Okay. Remember we had discussed that if the change in pressure is high, then you can use the compressibility relation to identify if your density change is also important, right, and then you can call this flow as compressible, right. So, you can actually further cast it for an isentropic flow, because that is also a reasonable assumption, as we have discussed earlier, that if the flow does not have boundary layer, then you can assume it to be isentropic, because you are not adding any heat and there is no dissipation, viscous dissipation and all. So, in that case you will have, for the isentropic flow, we have derived the equation for speed of sound, okay, expression for the speed of sound, a square is equal to dp by dx, okay, for the isentropic flow, okay, dp by d rho. Okay. So, the dp in this, let us call this expression x. If you put in x, so then it will become rho u du is equal to minus a square d rho, right. So, now what I will do, I will multiply with u and divide with u. This is u square, and I will take a square on this side, a square du by u, take minus on this side will be d rho by rho, right. So, what is this? U by a, we have discussed it earlier, u by is equal to your Mach number. So, minus m square du by u is equal to d rho by rho, right. See, what we got here is the relation between your change in density, per unit density, with the change in velocity, per unit velocity, right, and you can see that it depends on your Mach number. Not only depends, but it strongly depends on the Mach number, because this is the proportionality constant is basically m square, right. So, if m is less than 1, okay, which is the case of subsonic flow. So, in that case your change in densities, this is d rho by d rho, or the change in density is very small, okay, you can just call it change in density is small with change in velocity compared to the change in velocity, right. When Mach is equal to 1, okay, which is the sonic flow, your change in density is basically equal to the change in velocity, right. If you change the velocity by certain amount, the density will also proportionally change by the same amount, right. This is small, here in this is equal to change in velocity, and when m is greater than 1, then it is supersonic flow. So, in that case your change in density is much greater than the change in velocity. So, that is why you can now understand that when you go to basically higher and higher Mach number, your density change becomes very important, and you cannot ignore the compressibility. Okay. In fact, I mean the general thumb rule is when the Mach number is greater than 0.3, okay, the change in density, which is d rho by rho, is basically more than 5%. Okay. The change in density is more than 5%, and because of that you cannot ignore the compressibility, and you have to basically use the compressible Navier-Stokes equations. Okay. Now, let us just finish with one final thought, okay, which is basically the incompressible flow, and we will start more discussion on incompressible flow in the next class. But just to give you an idea that in the case of incompressible flow, your del dot u is basically 0. Okay. So, that means basically del u k by del x k equal to 0, and that actually simplifies a lot of things. Okay. In the case of incompressible flow, your viscous stress term becomes very simple, okay, but then you also lose something in the sense that you can no longer use P equal to rho RT relation. Okay. Why? Because your density is constant, your temperature is constant. So, you will get a constant value, right. So, your pressure is not the thermodynamic pressure, but instead it is the mechanical pressure that we derived in the last class. Okay. So, we will look at the incompressible flow equations in the next class, and then we will continue from there. Okay. Thank you very much.